Okay, this is additional video on chapter 8, especially for some I think some essential questions and also practice. So first of all, I would like to start with the phase change that we have in a 8.4 in chapter 8. So we start with the questions. Okay, give you directly the scheme and the questions. Okay, now we have the question on liquid mixture of benzene and toluene that is going to be mixed, and we are going to heat. Okay, we are going to heat 50 degrees Celsius, so they have 10 degree, heat 50 degree, and they will have two product, liquid product and vapor product. Okay, so this will be for the benzene. So how much heat must be transferred to the mixture per gram mole of feed? So first thing that we can take is we start with drawing this diagram. We start with the 1 mole. Okay, 1 mole, and let's say we have because it's equimolar, we have half mole benzene and mole toluene, and we will have two streamlines. The first one is for vapor, the second one is for liquid. And based on the informations, we are having the vapor is 68.4 for the benzene, and the toluene will be the rest. Okay, so 1 minus 0.6, and the liquid is 0.4 for benzene and 0.6 for toluene. Okay, now to make sure that we are having all the informations correct, we could take the degree of freedom. So our unknown variables is three items: the mole of vapor, liquid, and the heat. Okay, and our objective is finding the heat, right? Then we have two material balance. Okay, we have the material balance and one energy balance. Okay. All right, now we could write down the first is the material balance for the benzene and toluene. So we have the total mass balance. The first steps is to realize that this mole is from 1 mole. Okay, for 1 mole becomes mole vapor and mole liquid, right? And the benzene is from 0.5, and this will be turns out to be 0.6 and 0.4. Okay, for the benzene. And we can solve this linear equations. We can take the NV is 1 minus NL, and then we could just substitute to here, and we get each of the mole for vapor and for liquid. Okay, and the energy balance is basically just Q, and it's equal to the change of the enthalpy. So we are going to have evaluation for the delta H, and we are going to make a table and put into our all the substance and make the reference. Okay, so the reference we take is benzene at the very early conditions, also at the toluene for the early conditions. Okay, so both of this will be our reference, so take it as 0. Okay. So we are going to compute the H1, 2, 3, and 4. Okay, so we are going to, based on the mole that we have, since we already make into this vapor and liquid, then we can make another calculation for the enthalpy. Okay, let me make into the next page. Okay, now the enthalpy that we have. So this is based on table B1 and B2. for the CP and also for some heat of vaporization in B1. Okay. So this B1 is usually heat of vaporization, and B2 is for CP. Okay, and for all the H1, 2, 3, and 4, especially for 1 and 2, this is just because it's basically the benzene for the liquid. Okay, so we are just taking not really that complicated way, but for H3 and 4, because there is some liquid vapor change or phase change, we would like to include this heat of vaporizations. Okay, and then this is the boiling point for each of the benzene and toluene. Okay, so this will be a benzene and toluene, right? And also we have the vapor. So this is the vapor one. Vapor. This is just a liquid, right? This is just liquid. So for H3 and 4, we need to include the vapor. Okay, the vapor, and we get all the numbers. We get all the numbers, and thus the energy balance, we just multiply all the moles with the H, the specific enthalpy, and then minus the input. Okay, so output minus input, we get the heat that we are going to have is 17.7 kilojoule. Okay, that's the 8.4, the partial vaporization. So basically what this is about is, if you have a liquid and then the liquid is having a phase change to vapor, then we are going to have this is what we call the partial vaporizations. Okay, so not all liquids becomes vapor, but we still need to include the calculations through this, especially this H3 and H4. Okay. Okay, next is I would like to give you another additional that is about the mixing. Okay, these solutions and mixing. Okay, the case is a production of HCl, the hydrochloric acid. So we are going to create the HCl by absorptions. Okay, so absorb the gases from in the water, the gases HCl in the water. So the question is asking, calculate the heat that must be transferred. So we are going to absorb the gas, and it will be, we are going to need some energy to transfer, right? And we have the conditions that the temperature is 100 degrees Celsius and the liquid water is 25 Celsius, and we are going to produce 1000 kilogram per hour, 28% of HCl, aqueous HCl at 40 degrees Celsius. So first of all, what we are going to produce is, let me just take this as our objectives. Okay, we would like to produce this. Okay, and let me go through, and by doing that, we are going to take it into our molar flow. So the molar flow that we are going to have is, first, the 28%, we could take it as 0.2 kilogram. Okay, and then calculate, and we mention how much mole that we need for HCl per hour. So we get 5,480. Okay, this is the molecular weight, right? Molecular weight. And also for water. So for water, this will be the 80%, 80% of the solutions, and we get this is about 44,400 moles. Okay, and I think this is quite correct, quite true, because of course the water is a solvent, right? It's a solvent. The next thing is we are going to put all the moles into our diagram. So this is the absorber, the gas absorber that we are going to observe. The absorber, it has some heat that we are going to measure. Now we have the mole of HCl, the mole for the water, and we have our objective. We need to produce this 1000 kilogram per hour, 28% of HCl at 40 degrees of Celsius. Okay, it has two different temperature for each substance, and we have the final temperature, right? Okay, now next, after we set the diagram, what we are going to do is we set up the reference and put all the information into a table of moles and specific enthalpy. So first, we are going to take the reference, the HCl H2O at 25 degrees and 1 atmosphere. So this means that the H2O, because it's 25 degrees Celsius, it's going to be 0. So we are going to calculate the H1 and H2. So H1 we are going to get from table B2. We're going to take CP from table B2, and this will be the result, 2.178 kilojoule per mole, the temperature from 25 to 100. Okay. Okay, and then after that, what we have is, before that, we need to calculate for the product solutions. So in this solution, the important thing is there will be some R, which is the ratio between moles of solvent and solute. Okay, so we are having 400 mole H2O and 5480 mole of HCl. If we compare this will give you 8.1 ratio. Okay. Now this 8.1, we are going to take it into table B11. So the HCl, the gases, plus 8.1, we make a stoichiometric reactions. Liquid 25 degrees Celsius. It has some change for the enthalpy, and we get it's become from gas become aqueous, or it's become absorbed into the chamber, and then so this, let's say this is A, this is B, and then the HCl increase in temperature. Okay. Now we get the delta H for delta HA. This is from the table B11. We get that this will be equal to delta HS, which is this is standard in temperature room, and also R is 8.1. You can check in table B11. And we got the number is 67.4 kilojoule per mole of HCl. Okay, now we take the mole fraction of HCl. This will brings to the mole of HCl per hour divided by the whole moles. Sorry, should be mole per hour. This will be 0.11 mole HCl per mole. Okay, and then from here we take the CP, we calculate for finding the delta HB. This is 0.73 kilocalorie. We need to take some conversions first. Some conversion for calorie and joule. And we get the CP is 0.557 kilojoule per mole SCl degrees Celsius. Now we get the delta HB, okay, that is from 25 to 40 degrees Celsius. CPDT. So using the CP that we approximate, we get it's 8.36 kilojoule per mole of HCl, and plus the delta HA, which is negative. So negative 67.4. This will give about negative 59 kilojoule per mole of HCl. Okay, so this is H2. This is H2. So we go back here. So we have H1, H2. Then the energy balance. We can put down the final informations, and based on what we have, the moles, the enthalpy that we have, we get this number. So this number is the heat that must be transferred out of absorber. The heat rate transferred out of absorber to keep the product temperature. Okay. So it should be 40 degrees Celsius. Okay. Okay, now we have questions. This is example questions on the enthalpy for two-phase system. So this will be on the chapter 8, 8.5. This is the ammonia concentration enthalpy chart. So let me just give you a brief through the questions. You have the ammonia solutions is equilibrium with vapor phase in closed system at 160 Fahrenheit, 1 atmosphere. Liquid phase is 95%. And determine the weight percent, of ammonia in each phase, and the enthalpy of the system per unit mass of the system content. So first is we're going to take the chart. Okay. So first we are going to take the 160 line, 160 degree Fahrenheit line, which is this line. Okay. And then the liquid phase liquid phase is 95%. So we could have the liquid phase is 95%. So we could have this is around 8%. And this part is around probably 65, 64, so maybe 64%. Okay. So on the liquid phase, is 8% ammonia and 92% of water, right? And this is around the enthalpy of the liquid is probably 110. And the vapor, we get 64% ammonia and 36% of water. And the vapor is around here, around 855 BTU over LPM. So if we take the basis of 1 LBM, total mass, so we could have 0.95 LBM liquid and 0.05 LBM vapor. Now the enthalpy is 0.95 multiply the 110 plus 0.05 multiply with the 855, and we get the result is this. Okay, so this is another how to use this the enthalpy concentration chart. Okay, now I will go for some practice. Okay, now looking at this number 27. So number 27. Okay, let me go take the screenshot and make a quickly. Okay, and then let's put all into here. Okay. Okay. Now we have a gas containing water vapor. It has dry basis composition of 8.5 mole percent of carbon monoxide, 10.5% carbon dioxide, 0.5% oxygen, and 80.5% of nitrogen. Okay, and then the gas leaves catalyst at 620 degrees Celsius, 1 atmosphere, with a dew point of 57 degrees Celsius at a flow rate of 28.5 SCMH. SCMH is standard cubic meters per hour. Or we could just take notes on this unit. Okay, so I don't think you need to know what is this, but just take the notes of what the unit is. Okay. So fallible solid catalyst particles entrained in the gas are to be recovered in an electrostatic precipitator, but the gas must first be cooled to 425 degrees Celsius to prevent damage to the precipitator electrodes. The cooling accomplished by spraying water at 20 degrees Celsius into the gas. So we need to use the material energy balance for the spray cooler to calculate the required water feed rate. So this is what we are going to achieve for the first goal. And the assumption is adiabatic. Neglect heat transfer from the entrained solid as they cool. So we just focus on the other way around. Okay, so we need to just neglect the heat transfer from the solid particles. And then okay, the second question is later we can discuss. So first, what we can do is we are going to build the diagram as usual. But before that, what we are having in the system is first we are going to see that at 57 this having a dew point. Okay, dew point. What is a dew point? Dew point is the first time that the water will comes out, right? Will comes out. So the dew point, the temperature that which air must be cooled to become saturated with water vapor. So basically what this means is at this 57 degrees Celsius we could take our calculations to find the water vapor or the pressure, vapor pressure. So we could take this at 57 degrees Celsius using this equation. So we get at 57 degrees Celsius, this is what we have. And we are having the mole of water per 1 mole. Okay, so we have a fraction of water as 0.171. The next thing is we have the 28.5. This is the moles. Okay, we could get the moles. Okay, the moles for water also. So 28.5 meter cube over hour. This is at the standard temperature pressure. So we could convert first and finding the mole by dividing with 0.02022 for meter cube. Okay, this is STP conversions, and this will equal to this mole per hour. Okay. And based on what we have here, so we get that this will turns out to be 217.2 mole H2O per hour. So we find from our fractions. Okay, so this is a fraction. Or if we want to make it into a kilogram per hour, we could make it and exchange the water. Okay. So we have 1,270 mole per hour. We could minus the water, which is 217.2, and we get the result is our gas. Okay, our dry gas. And we have a percentage based on the questions. So 89.5 CO per hour, 110.5 CO2 per hour, right? So, okay, based on the percentage, so 8.5 mole percent, then 0.5, 0.5, and 80.5. So nitrogen should be the highest one. So this will be oxygen. mole, for I think the mole of oxygen per hour. This is 847.6 mole nitrogen per hour. Okay, and then take the diagram. This will be the temperature at the beginning and the total mole and the mass for water liquid per hour. Okay. And this will be 20 degrees Celsius. This is the one that we are going to use for cooling, right? For cooling. So this is the cooling accomplished by spraying water, blah blah blah, right? Okay. So we might need a reference. We might need a reference. So we have a substance, the mole in, the specific enthalpy for in, the mole out, specific enthalpy out. Okay, this first substance is CO. It's 89.5. This is CO2, 1. Oxygen, this will be 5.3. And nitrogen, this is 847.6. Okay, we take table, table P8 okay, to check the gas, okay, the gas CO, CO2, oxygen, and nitrogen. And we get the results for the specific enthalpy is 18.22, 27.6, 19.1, and 18.03. All the enthalpy is in the kilojoule per mole. Okay, kilojoule per mole. The mole is mole per hour. Okay, and then it's the same. And the enthalpy out. We get also from okay, now at the 425, right? 425. This is for the specific enthalpy out. In the table B8, what you need to do is because in table B8 the temperature is from 0, 25, 100, 200, 300 until 1500. There is no 420. What you can do is you can make some take extrapolations, right? Okay, take extrapolation and maybe approach with a linear equation, right? That will be having a much more approximately okay number, okay, for the enthalpy. So from that method we get this is 12.003, 17.6, 12.54, 11.90. Okay, now we have the water for the vapor and water for the liquid. Now water for the vapor, at the beginning it's around 3.91. Okay, that's the initial conditions, and we don't know the flow rate when it's going the liquid one. Okay, and we also need to check the steam tables. Okay, check table B6, B7, right? Is that superheated? I think just saturated, right? Okay. So I think just check the steam tables, and you get this is 3,749. Okay, let me check. I think it's correct. Yeah, I think we get the number is around 3749. So again, it's using the same techniques, extrapolation. So it's also extrapolations for stream extrapolation for steam tables. Okay. So you maybe taking 7, 8 data and then make the linear equation and take out this 620. Okay, and this one is 83.9 for the liquid one, and the molar out we have plus nothing here, and the enthalpy is 3,330 kilojoule per mole. It's the same thing with using the extrapolations. Now from here, we would like to compute then the delta H. Okay. I think I will just erase this part. Okay, let me just erase this whole part here. So we have the delta H by taking the calculations for all the moles and the enthalpy. This will be equal to now why is this is 0? Because it's, remember, it's adiabatic. Okay, Q is 0. So we got M is equal to 0.62 kilogram per hour. Okay, so this is table B8, B7, and table B11 for the, yeah, I think B8, B7, yeah, just B8, B7, yeah. Okay. In terms that a high school senior could understand, explain the operation of the spray cooler in this problem. What happens when the cold water contacts the hot gas? Okay. So the cold water, okay, this is the blue one, the cold water. Let's say this is cold water. And this is the gas, hot gas. So what is happening here? So if this is going to contact with the water, then first of all the heat transferred, right? The heat transferred from gas to water, right? And then first is the gas, the T is lower, right? The T is lowering, and water, the T is rising. Okay, just as simple as that. Okay, that's 8.27. Okay, another example is about the cychromatic chart. So cychromatic chart, okay, if you see the chart here, let me just go through the example first. We have air at some dry bulb temperature. We have this 10% humidity. It's going to be humidified adiabatically to 60% of humidity. And using the chart to estimate the adiabatic saturation temperature, or this is the wet bulb temperature, right? If you remember the terms. And then the second question is final temperature of the air and rate at which water must be added to humidify this much of air. Okay, now by looking at the given informations, that we start from 45 and 10% humidity. So for 45, this is 45 and 10% humidity is here. So maybe you could take this line and take another line here. So probably this will be around from the chart we get the absolute humidity is 0.00. I think it's just 59, okay, because it's a little bit below the 6. So kilogram H2O over kilogram of dry air, right? And then the wet bulb temperature, we could take this and take it into here. So this will be around 21, right? 21 degrees Celsius. So temperature of wet bulb is 21 degrees Celsius. Okay, that's the first options. And the second one that we have is, because we have 21 wet bulb, and we would like to have the humidity on 60% relative humidity. So this will be 60% is here. Okay. So we could get another subject through here, right? So that's supposed to be around 27. And we could take that as 27. So the temperature, when we have temperature wet bulb is 21, the dry bulb, and the relative is 60%. The temperature of dry bulb that we are going to have is around 27 degrees Celsius. So from this 27, we would like to compute, okay? So we will have around 0.0135, right? All right, now we could take this H. Oh, sorry. Okay. Okay. And we can take the absolute humidity is around 0.00135 perhaps. And then the question is, we need to have this, right? The humidify this 15 kilogram per minute. So H2O, oh, sorry. This is 1.0059 kilogram air. This is from this plus one, right? And then multiply with this subtractions of 0.0135 minus 0.0059, 1 kilogram dA, 1 kilogram H2O. This will resulting in 0. How much is it? Around 11, right? That's how we got